40 light-years away, 7 worlds are circling a star so small and so dim that for most of human history, we did not even know it existed. 7 planets, all of them roughly the same size as Earth. All of them sitting in the zone where liquid water could survive. Scientists called it the most exciting system ever discovered. They said it was our best chance of finding life beyond our solar system. They ran every test they could think of, and for years, TRAPPIST-1 passed every single one. But Webb looked closer, and what it found forced researchers to rethink everything. If you enjoy this, like and subscribe. Take a breath. We launch into the deep. There is a star in the constellation Aquarius, so faint that even with a decent telescope, you would probably miss it entirely. It does not blaze the way most stars do. It does not even glow with the kind of warm light we associate with distant stellar fires. It burns a deep, dull red, giving off less than 0.1% of the energy our own star releases into space each second. For most of human history, TRAPPIST-1 was effectively invisible to us. Not because it was far away by cosmic standards, it is actually relatively close, sitting just 40 light-years from Earth. But because it is so extraordinarily dim, it slipped past centuries of stargazers without a single second look. That changed in 2017 when a team of astronomers using a small Belgian telescope called the Transiting Planets and Planetesimals small telescope announced something that stopped the scientific world cold. They had found not 1, not 2, but 7 planets orbiting this forgotten red dwarf, 7 worlds, all of them close to the size of Earth, all of them sitting in a tight cluster around their parent star. The announcement made headlines everywhere. Scientists called it unprecedented. Researchers said it was the most important planetary discovery in a generation. And buried deep inside, the excitement was a question that nobody could quite answer yet. Could any of them be alive? The star itself is what astronomers call an ultra-cool red dwarf. These are the most common type of star in the entire galaxy. Roughly 3/4 of all stars are red dwarfs. They burn slowly, gently, and for an almost unimaginable length of time. While our own star will exhaust its fuel in roughly 5 billion more years, a star like TRAPPIST-1 could keep burning for 10 trillion years. That is nearly 1,000 times the current age of the universe. If life needs time to develop, and most scientists believe it does, then red dwarfs offer something more familiar stars cannot. Patience on a scale that makes the history of everything we have ever known look like a single afternoon. But patience alone does not make a system habitable. The 7 planets of TRAPPIST-1 are packed so tightly around their star that all of them complete their orbits in less than 20 Earth days. The outermost planet takes only 18.5 days to circle the star once. Compare that to Earth, which takes 365 days to complete a single orbit. These worlds are crammed into a space smaller than the distance between our own star and the planet Mercury. They are close, extraordinarily close, and that closeness, combined with the nature of the star at the center, creates a set of conditions scientists have been arguing about intensely ever since. Somewhere in that tight, glowing cluster of worlds, 3 planets sat inside what astronomers call the habitable zone, the region where temperatures might allow liquid water to pool and persist on a surface. And where there is liquid water, there is always, at least in principle, the possibility of something far more remarkable than bare rock and empty sky. But what Webb eventually found about that habitable zone would not be what anyone had expected, and the discovery would change how scientists think about the most common type of star in the entire galaxy. Most star systems keep their habitable zone planets scattered and lonely. Our own solar system has only one world sitting comfortably in that warm middle band where liquid water can pool on the surface. Mars skirts the outer edge and came up cold. Venus bakes on the inner side and boiled its oceans away billions of years ago, Earth alone landed in the right spot and held on. So the idea of a star system with 3 planets simultaneously sitting inside the habitable zone felt almost too good to be true. Scientists ran the numbers again and again. The numbers kept coming back the same way. TRAPPIST-1, E, F, and G are the 3 worlds that grabbed attention immediately. Scientists labeled them the prime candidates. They are rocky, like Earth. They are small enough to potentially hold onto atmospheres over long timescales, and they sit at distances from their star where the temperatures, at least on paper, should allow water to exist in liquid form on the surface. Planet E was quickly described as the most Earth-like planet ever discovered outside our solar system. It receives almost exactly the same amount of energy from its star as Earth receives from ours. If you could swap it with our planet in terms of pure energy budget, the numbers line up almost perfectly. The excitement around these 3 worlds was not just scientific enthusiasm. It was something closer to genuine, almost breathless hope. For the first time in the history of astronomy, researchers had multiple Earth-sized planets in a single system where the conditions for life might exist simultaneously. Some scientists floated the idea that TRAPPIST-1 could be a kind of biological relay system. If life emerged on one of these worlds, it might have spread to the others through a process called panspermia, where microbes travel between planets on rocks ejected by ancient asteroid impacts, drifting through space until gravity pulls them somewhere new. But there was a problem quietly nagging at the back of every optimistic headline. The planets of TRAPPIST-1 are not just close to their star in a general sense, they are extremely close. So close that most of them are almost certainly tidally locked, meaning one side of each planet permanently faces the star while the other side sits in permanent darkness. The daylit side would bake under a relentless flood of radiation. The night side would freeze in total, unending darkness. Whether life could survive at the boundary between those 2 extremes, in a thin strip of twilight that wraps around each planet like a belt, was something nobody could answer from a distance of 40 light years. Something else was quietly worrying researchers. TRAPPIST-1 might be small and cool, but it is not quiet, not even slightly. Red dwarf stars are known for violent, unpredictable behavior. They flare constantly. And those flares are not gentle. They blast out intense radiation and charged particles in surges powerful enough to strip the atmosphere from an unprotected planet in what amounts to a geological blink. Whether the TRAPPIST-1 planets had any protection from that relentless fury was the question that would eventually send Webb into the darkness to find out. Imagine waking up every single morning to a sunrise that simultaneously sets your sky on fire. Not metaphorically, literally. A pulse of radiation so intense that it would scramble electronics, shred the molecular chains that make up biological material, and push the upper layers of your atmosphere out into the void of space. For the planets of TRAPPIST-1, this is not a rare catastrophe. It is not even a notable event. It is simply Tuesday. Red dwarf stars flare. That is a well-known fact in astronomy and has been for decades. But the degree to which TRAPPIST-1 in particular bombards its planets with radiation was not fully appreciated until researchers started paying very close attention with modern instruments. In some observed periods, the star unleashes dozens of significant flares within a single day. Some of these events release as much energy as the most powerful flares ever recorded from our own star, but they are compressed into a much smaller system where the planets sit far, far closer to the source. The effect on those worlds is orders of magnitude more severe. When high-energy radiation and charged particles slam into the upper atmosphere of a planet, they begin breaking apart molecules and ionizing gases. This strips lighter elements away from the planet's gravitational grip and gradually pushes atmospheric material out into space in a process called atmospheric erosion. For a planet close to an active star with no protection, this process can strip away an entire atmosphere over tens or hundreds of millions of years. Compared to the 10 trillion year lifespan of a red dwarf, that window of time is remarkably, terrifyingly short. This raised an uncomfortable question about the TRAPPIST-1 system specifically. These planets have been circling their star for an estimated 8 billion years. That is almost twice the current age of our own solar system. They have had 8 billion years of exposure to flares, to radiation bursts, to streams of charged particles washing over them day after day after day. If their atmospheres were ever vulnerable to this kind of assault, and there is compelling reason to believe some of them were, then 8 billion years is more than sufficient time to scrub them completely clean. But here is where the story gets genuinely complicated. Planets with strong magnetic fields can deflect incoming charged particles the same way Earth's magnetic field deflects the stream of particles flowing from our own star and channels them into the glowing auroras we see at the poles. If the TRAPPIST-1 planets have magnetic fields, they might have held onto their atmospheres despite the constant assault. Whether they actually possess such fields was one of the central mysteries Webb was built to help answer. Magnetic fields are almost impossible to detect directly from 40 light-years away. What you can do is look for side effects. An atmosphere absorbs starlight in specific ways depending on what molecules it contains. If Webb could analyze the light filtering through whatever atmosphere remained, it might be able to tell whether anything was left at all. TRAPPIST-1 was first in line, and the answer it returned was not what the team had hoped for. The James Webb Space Telescope was not designed with TRAPPIST-1 in mind as its primary mission. But from the moment it reached its position 1 million miles from Earth and began cooling its golden mirrors to temperatures near absolute zero, researchers knew this system would be among the first and most important targets. Webb is the most powerful space telescope ever put into operation. Its primary mirror spans 21 feet across. It detects infrared light with a sensitivity so extreme that it can analyze the chemical signature of an atmosphere on a planet dozens of light years away. In theory, in practice, doing that around a star as dim and magnetically active as TRAPPIST-1 was going to be a serious and complicated challenge that would push the instrument to its limits. The technique Webb uses for atmosphere detection is called transmission spectroscopy. When a planet passes between Earth and its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching Webb's detectors. Different molecules absorb different wavelengths of that light. Carbon dioxide leaves one distinct fingerprint in the spectrum. Water vapor leaves another. Methane, oxygen, and nitrogen each mark the spectrum in their own specific way. By comparing the starlight during a transit to the starlight, when the planet is not in the way, astronomers can subtract out the planet's contribution and read what chemicals are present in its atmosphere. This technique works with extraordinary precision for large gas giant planets wrapped in thick, chemically rich atmospheres. It becomes dramatically harder for small rocky worlds where the atmosphere, if one exists at all, is thin and produces only a faint signal. The difference in signal strength between a gas giant and a rocky world can be a factor of hundreds, but Webb's sensitivity was designed precisely for this kind of challenge. Researchers were cautiously, carefully optimistic as they finalized the observation plans. The first TRAPPIST-1 planet they targeted was Planet B, the innermost of the 7. Planet B is not in the habitable zone. It orbits too close to the star and bakes at temperatures almost certainly far too high for liquid water to exist anywhere on its surface. But it was the easiest target for an initial observation campaign precisely because of that tight orbit. Its transits are frequent, since it circles the star in under 2 Earth days, which meant Webb could stack many transit observations quickly and build a reliable statistical picture of whatever signal, if any, existed. The scientific team waiting for the results was large, spread across multiple countries, and operating on a mixture of professional discipline and barely contained excitement. Some members had spent years writing the observation proposals, Others had built the atmospheric models that would interpret whatever Webb returned. For the community of researchers who had devoted careers to the TRAPPIST-1 system, this was the moment they had been working toward for years. The data came back. The team analyzed it. And then things started getting strange, because what Webb found on Planet B did not match any of the models built for a world wrapped in a thick, protective atmosphere. The numbers pointed somewhere else, somewhere colder, somewhere emptier than almost anyone had wanted to believe. The inner planet of TRAPPIST-1 was never supposed to be the crown jewel of the system. Planet B orbits so close to its star that even accounting for the star's relatively dim nature, the energy hitting its surface is roughly 800 times what Earth receives from our own star. That is scorching on a scale that makes Venus look temperate by comparison. Researchers expected it to be something like Venus at best, a world smothered under a thick blanket of carbon dioxide with surface temperatures capable of melting lead. Some models even predicted it might have vast pools of liquid magma on its star-facing side, an ocean of molten rock sitting under a permanently blazing point of red light that never moves from the same spot in the sky. What Webb actually measured was something that neither of those models could fully explain. Using its mid-infrared instrument, Webb measured the thermal emission from Planet B directly, meaning it measured the heat radiating off the planet's surface and reaching the telescope across 40 light-years of empty space. The technique is called secondary eclipse photometry. You measure the combined brightness of the star and planet together, then measure the brightness again when the planet passes behind the star and only the star's own light is reaching the detector. The difference between those two measurements tells you exactly how much heat the planet itself is radiating into space. The temperature Webb measured for the day side of Planet B came back around 230 degrees Celsius. That sounds extremely hot, and it certainly is. But here is the critical detail. A planet with a thick atmosphere like Venus traps heat through the greenhouse effect and amplifies surface temperatures far beyond what the raw energy input alone would produce. Venus reaches nearly 500 degrees at its surface precisely because of this trapping and amplifying effect. Planet B should have been dramatically hotter than 230 degrees if anything substantial was holding heat in around it. The measured temperature was instead consistent with what you would calculate for a bare rock with no atmosphere at all, a world absorbing starlight directly and radiating that heat straight back out into space with nothing in between to amplify or retain it. A planet stripped of its atmosphere cannot support liquid water anywhere on its surface. It cannot support the sustained chemical reactions that life as we understand it requires to function and persist. It cannot be anything other than a dead, airless rock turning under the light of its star. And if the innermost planet had lost its atmosphere entirely after billions of years of radiation bombardment, the next question was immediate and unavoidable. What had happened to the others sitting farther out? Researchers were careful not to draw broad conclusions from a single planet's data. Planet B was always the weakest candidate in the system, the one sitting closest to the radiation source and absorbing the most punishment. Perhaps the inner planets had always been too exposed for any atmosphere to survive. The real question was what Webb would find when it turned toward the planets that actually sat in the habitable zone itself. Planet C was next, and it came back with an answer almost identical to B. The pattern had begun. When scientists get a result they do not want, the first thing they do is check whether it might be a measurement error. They look at the models. They look at the instrument calibration. They look for any alternative explanation that might rescue the hopeful scenario. Maybe something unusual about Planet B made it an outlier. Maybe the inner planets had always been too close to the star to be representative of the system as a whole. When Planet C came back with almost exactly the same story as Planet B, the uncomfortable question became considerably harder to explain away. Planet C orbits slightly farther from the star than Planet B, completing one full orbit every 2.5 Earth days. It still sits well inside the habitable zone, still too close and too hot for liquid water to persist on its surface over any meaningful length of time. But by the logic of gradual improvement through distance, Planet C should have fared at least somewhat better. A little more separation from the star means slightly less direct radiation. A little more time between radiation bursts means a slightly greater chance for an atmosphere to stabilize and hold. Some researchers entered the analysis expecting Planet C to show at least a faint atmospheric signal, even a thin one that might hint at something surviving. Webb's secondary eclipse measurement for Planet C came back pointing toward the same conclusion as Planet B. The dayside temperature was consistent with a bare rock without insulating gases wrapped around it. If Planet C retained an atmosphere, it was either extraordinarily thin or composed of something so unusual that it did not trap heat the way standard atmospheric gases do. The explanation that matched the numbers most cleanly was the same one that had emerged from the Planet B data. No substantial atmosphere, bare rock, open sky, 2 planets, both pointing toward the same verdict. The scientific team began updating their models and their expectations. Some researchers started drafting papers about what these results might mean for the habitability of the outer planets. Others pushed back. They pointed out, correctly, that 2 data points do not establish a pattern by the standards of rigorous science. They pointed out that planets B and C were always the long shots, the ones closest to the stellar fire. The 3 genuine habitable zone planets, E, F, and G, were still untested. Those were the ones that actually mattered for the central question. But something else in the early results had revealed a subtler and more troubling sign. The data from planets B and C showed almost no evidence of high albedo, meaning the planets were absorbing most of the starlight hitting them, rather than reflecting it back into space. A planet covered in bright clouds or snow reflects a large fraction of incoming light and therefore runs cooler than you might otherwise expect. A planet with no clouds absorbs almost everything and runs hotter. The TRAPPIST-1 inner planets appeared to be absorbing almost all of the starlight reaching them. No clouds meant no weather. No weather strongly suggested no substantial atmosphere generating any of it. 3 habitable zone planets were still waiting their turn, but the momentum of the evidence was no longer pointing toward hope. Before Webb delivered its verdicts on the habitable zone planets, scientists were already wrestling with a fundamental problem that had nothing to do with atmospheric chemistry. It had to do with rotation, or more precisely, the near total absence of it on most of these worlds. Tidal locking is what happens when the gravitational pull of a massive nearby body gradually slows the rotation of a smaller orbiting object until that object rotates at exactly the same rate as it orbits. The result is that one face of the smaller body always points toward the larger one, and the other face always points away. Our own moon is the most familiar example. The same hemisphere of the moon always faces Earth. The other side, which we call the far side, perpetually faces the outer darkness of space. Gravity, working across billions of years of patient friction, caused this arrangement to settle into place and locked it there. The TRAPPIST-1 planets are almost certainly in the same situation with their star, though in this case the locked face points toward the star rather than away from it. For a moon, tidal locking is an interesting orbital curiosity. For a planet that might be trying to support liquid water and complex chemistry, it is a fundamental reshaping of everything we would normally consider necessary for habitability. The day side of a tidally locked world receives a constant, unrelenting flood of starlight and heat, with no rotation to spread that energy around the globe. The night side sits in permanent, absolute darkness and permanent cold, temperatures potentially plunging hundreds of degrees below the freezing point of water. Between those 2 extremes, wrapping around the planet like a thin ribbon, sits a narrow terminator zone where day meets night, where temperatures might be more moderate and conditions slightly less extreme. Some researchers have proposed that the terminator zone of a tidally locked planet could actually be viable for life. Temperatures there might remain relatively stable across geological time. Water could potentially pool in liquid form in sheltered regions. Winds carrying moisture from one hemisphere to the other might create a thin circulation that keeps the terminator from freezing or baking entirely. A few carefully constructed scientific papers have modeled what ecosystems in such a place might look like. Life huddled in the permanent twilight of a world that never sees a true sunrise or a true sunset, only a dull red star hanging forever motionless at the horizon. It is a compelling and genuinely moving image, but it depends on a crucial assumption. It depends on the planet retaining an atmosphere thick enough to drive that circulation across the globe in the first place. A thin atmosphere cannot transport heat efficiently from the day side to the night side. Without that heat redistribution, the night side freezes solid over time, ice accumulates, the water cycle collapses, and the terminator zone that might have offered some moderate refuge gets squeezed and destabilized until nothing hospitable remains. The atmosphere question and the tidal locking question were not separate issues at all. They were the same issue wearing different clothes, and Webb was about to answer it for the world researchers had pinned their deepest hopes on. If you had to choose one world in the TRAPPIST-1 system to place the weight of scientific hope upon, almost every researcher who studied this system between 2017 and 2023 would have named the same planet, Planet E. They described it as the most Earth-like world ever identified outside our solar system. The energy it receives from its star is nearly identical to what Earth receives from ours. Its size and mass fall close to Earth's own values. Its density strongly suggests a rocky interior. On paper, in terms of pure energy budget and fundamental physical characteristics, Planet E sat at the top of every habitability ranking ever published about this system. Nothing else in the entire known catalogue of exoplanets came quite as close to checking every basic box simultaneously. The emotional weight behind Webb's observations of Planet E was genuinely different from the earlier measurements of the inner planets. Those had always been long shots. The planets everyone understood were probably too close and too battered to hold on to much. Planet E was different in kind, not just in degree. Researchers who had spent entire careers building the scientific case for red dwarf habitability entered the observation window with a level of attention and personal investment that went beyond ordinary professional procedure. The telescope gathered data across multiple transits, stacking the signal one measurement at a time until statistical confidence reached an interpretable level. The initial results were more ambiguous than those for planets B and C. The signal was genuinely harder to read with confidence. TRAPPIST-1's constant variability, its flickering surface, and its irregular flaring introduced noise into the data that required sophisticated modeling to subtract before anything planetary below it could be seen clearly. Some team members initially thought they detected faint features in the spectrum that might correspond to atmospheric molecules. Papers began to take shape. Conversations in research offices grew carefully and cautiously excited. But as the analysis deepened and additional observation campaigns contributed more data, the picture gradually clarified in a direction nobody had been eager to see. What had initially appeared as potential atmospheric signals were most likely artifacts of stellar contamination, meaning the star's own variability was creating false features in the spectrum that closely resembled the signature of genuine atmospheric molecules. When researchers applied their best models of stellar surface behavior and corrected for its contribution, the planetary atmospheric signal shrank towards something vanishingly small. The best current interpretation suggests Planet E either has no substantial atmosphere or retains one so extraordinarily thin that it provides almost no radiation protection and almost no ability to moderate the extreme temperature. Contrast between its permanent day side and its permanent night side. For a tidally locked world in the habitable zone, that conclusion effectively forecloses the conventional picture of surface habitability. The crown jewel of the TRAPPIST-1 system had cracked under measurement. 2 planets remained in the habitable zone, and one of them was holding something that would briefly reignite the scientific conversation and force researchers to revisit every assumption they had brought into the campaign. But it would also raise a new and more complicated set of questions than anyone had anticipated. In the years immediately following the TRAPPIST-1 discovery, a group of researchers put forward an idea that captured public imagination almost immediately and spread through science journalism with remarkable speed. What if several of the outer planets in this system were not just covered in liquid water oceans, but were almost entirely ocean worlds? Their surfaces submerged under water so deep that no dry land existed anywhere on the globe. The idea was grounded in density measurements. When you calculate the mass and size of a planet precisely, you can derive its average density. If a planet's density comes back lower than you would expect for pure rock, something less dense must be making up a significant fraction of its volume. Water ice is substantially less dense than rock. A planet containing a very large fraction of its total mass in the form of water would have a measurably lower average density than a purely rocky world of the same size. Several TRAPPIST-1 planets had densities that seemed to fit this picture, suggesting they might contain anywhere up to 5% of their total mass in water. 5% sounds like a small number, but applied to a planet roughly the size of Earth, that fraction represents an ocean hundreds of kilometers deep. For comparison, Earth's oceans represent less than 1/10 of 1% of our planet's total mass and average roughly 4 kilometers in depth. A planet with 5% water by mass would have oceans so impossibly deep that the pressure at their floors would compress water into exotic, crystalline forms of high-pressure ice that do not exist naturally anywhere on Earth. There would be no beaches, no coastlines, no continents, just water extending endlessly down into darkness and pressure. This is scientifically interesting for habitability because water is, as far as we know from direct observation, a fundamental requirement for life as chemistry can produce it. But an ocean world with no dry land and no interface between rock and water at the surface might be a very different environment from the ones in which life actually arose on Earth. The chemistry that happens at the boundary between rock and liquid water, where minerals dissolve and concentrate and react, may have been crucial to the origin of biology on our planet. Some researchers believe life on a deep ocean world is perfectly possible. Others remain genuinely skeptical. More importantly, for the TRAPPIST-1 debate, the ocean hypothesis ran into a problem that Webb's observations sharpened considerably. A planet with a vast, warm, global liquid water ocean would be evaporating water constantly into its atmosphere. You would expect to see a clear, strong water vapor signature in the spectrum, a chemical fingerprint that Webb is particularly sensitive to detecting. Webb did not find that signature clearly in the habitable zone planets. The water signal that a genuine ocean world should have been broadcasting was conspicuously absent from the data. Whatever water these planets possess might be locked in subsurface ice, hidden deep underground, or simply gone, burned away by billions of years of radiation. The ocean world's picture, as appealing as it was to imagine, was becoming harder and harder to reconcile with what the telescope was actually measuring. And then researchers turned their attention more carefully to what the star itself was doing during all of these measurements. While Webb was trying to read the atmospheres of the TRAPPIST-1 planets, something kept interfering with the data in ways that were impossible to ignore. The star itself, TRAPPIST-1, was not sitting quietly in the background while the telescope tried to do its work. It was erupting, constantly, unpredictably, and at a rate that surprised even researchers who had been studying red dwarf activity for years. And the scale of that stellar behavior was becoming one of the most significant findings of the entire observation campaign, not primarily because of what it meant for Webb's measurements, but because of what it revealed about the long-term environment these planets had been living in across 8 billion years. A stellar flare is essentially a magnetic explosion on a star's surface. When tangled magnetic field lines snap and reconnect in an energy-releasing cascade, they send a burst of radiation and charged particles out across the electromagnetic spectrum in every direction. For our own relatively calm and stable star, major flares are dramatic events that make international news. We track them carefully because of their potential to disrupt satellite operations and damage power infrastructure on Earth. For TRAPPIST-1, flaring is not a dramatic or newsworthy event. It is simply the default state of the star from one day to the next. During Webb's observation windows, the telescope recorded the star producing significant flares at rates that pushed the upper boundary of what researchers had anticipated, even from this notoriously active class of star. Some single observation sessions captured multiple major flares within the span of one day. These were not just producing excess visible light. They were pumping out intense ultraviolet radiation and energetic particles at levels that, for a planet sitting as close as TRAPPIST-1's worlds do, would translate to something like standing continuously next to a powerful radiation source with no shelter of any kind. The long-term consequence of this sustained bombardment is stark and well understood from basic physics. Over billions of years, a relentless rain of high-energy radiation breaks apart molecules in the upper atmosphere and strips hydrogen and other light elements from the planet's gravitational hold. It splits water molecules in the upper air into their constituent parts, hydrogen and oxygen. The hydrogen, being extremely light, drifts upward and leaks into space. The oxygen either follows or gets chemically absorbed into surface minerals. Run this process long enough, and you can drain an amount of water equivalent to entire Earth oceans from a planet's surface without leaving any obvious trace of where it went. Some models of the TRAPPIST-1 system suggest that over their 8 billion year history, the habitable zone planets may have collectively lost water volumes equivalent to dozens of Earth oceans to this slow but relentless atmospheric stripping. That is water that is not underground, not frozen at the poles, not locked in some geological reservoir. It is scattered into space, atom by atom, over geological timescales that stretch far beyond anything human minds were built to intuitively grasp. If those models are even approximately correct, the ocean worlds are not what these planets are now. They might be what these planets used to be billions of years ago, before the star had time to burn it all away. But could a magnetic field have changed that story? That question was still waiting for its answer. Every time a scientist raises the radiation problem facing TRAPPIST-1's planets, someone in the conversation raises the same counter-argument. Earth survives in a fairly hostile radiation environment too. Our own star produces flares. The stream of particles flowing outward from our star constantly pushes against the boundary of our atmosphere. And yet life here is not just surviving, but thriving in enormous complexity and diversity, protected in significant part by something completely invisible to the naked eye, but absolutely essential to everything alive on this planet: Earth's magnetic field. Earth's magnetic field is generated by the slow churning of liquid iron through our planet's outer core, a process geophysicists call the geodynamo. As that liquid iron circulates, driven by heat escaping from deep in the planet's interior, it generates an enormous invisible bubble of magnetic force called the magnetosphere. This bubble deflects the vast majority of charged particles streaming toward us, routing them around the planet through the polar regions where they create the aurora displays visible at high latitudes. Without this shield, our atmosphere would erode considerably faster than it currently does. Over billions of years, it might look more like Mars, which lost its own magnetic field early in its history and has since been slowly leaking its atmosphere into space, leaving a cold, thin, radiation-bathed surface. The obvious hope for TRAPPIST-1 is that at least some of its planets retained strong magnetic fields, and that those fields provided the protection needed to hold onto their atmospheres across 8 billion years of stellar bombardment. The problem is that magnetic fields are extraordinarily difficult to measure in distant planetary systems. Webb cannot detect a magnetic field directly from 40 light-years away. Neither can any other instrument currently in operation anywhere on Earth or in orbit. What researchers can do is look for indirect evidence that a magnetic field might be present. One promising approach involves looking for aurora-like radio emissions. When charged particles interact with a planetary magnetic field, the resulting energy can be released as radio waves at specific frequencies. Several research teams have pointed radio telescopes at the TRAPPIST-1 system, specifically searching for this kind of signal. The results so far have been genuinely inconclusive, neither definitively absent nor clearly present. Another approach is theoretical modeling. If you know a planet's size, composition, and likely internal heat output, you can estimate whether conditions are right for an active geodynamo. Here, the results for TRAPPIST-1 are not encouraging. Tidal locking affects more than just the surface temperature of a planet. The constant gravitational flexing from the star that causes tidal locking also affects the interior of the planet itself. Under some conditions, tidal heating can warm the interior enough to drive geological activity. Under other conditions, it can interfere with the convection patterns that power a geodynamo, potentially shutting down the magnetic field entirely. Whether any of the TRAPPIST-1 habitable zone planets have magnetic fields today remains genuinely, completely unknown. But the absence of clear atmospheric signals combined with the star's documented ferocity was pushing the scientific consensus in a direction that had seemed unreasonably pessimistic only a few years earlier. And then something in the outer system changed the conversation entirely. By the time Webb turned its primary attention to the outer habitable zone planets, the narrative of the observation campaign had taken on a clear and difficult shape. Inner planets had returned no atmosphere. The most celebrated middle planet had come back ambiguous at best. The star had documented itself as relentlessly hostile across every observation window researchers opened. The system was beginning to look less like a paradise of potential biology and more like a long, slow, cautionary tale about what radiation does to small rocky worlds across geological ages. Then something unexpected appeared in the data from Planet G. Planet G is the outermost of the 3 habitable zone worlds. It circles its star once every 12.5 Earth days. It receives less energy from TRAPPIST-1 than the inner habitable zone planets do, placing it toward the cooler outer edge of the region where liquid water might theoretically exist on a surface. Some researchers had worried Planet G might actually be too cold, that any surface water would freeze before it could remain liquid long enough to matter. Others reasoned that a sufficiently thick greenhouse atmosphere could raise surface temperatures to habitable levels even at that distance. In the Webb transmission spectroscopy data for Planet G, something appeared in the spectrum that had not shown up clearly in the data for any of the other planets. A faint but statistically interesting feature in the wavelength region specifically associated with carbon dioxide. Carbon dioxide is the molecule most commonly expected to dominate the atmospheres of rocky planets in habitable zones. Venus has enormous quantities of it. Mars retains a thin carbon dioxide envelope. Earth cycles it through biology and geology continuously. Finding any evidence of carbon dioxide in the spectrum of Planet G would not mean the planet is habitable by itself, but it would mean the planet has held onto at least some atmospheric gas. It would mean the relentless stellar radiation had not taken everything. The research team responded with deliberate, careful restraint. Stellar contamination remained a serious concern for this measurement as it did for all the others. The feature was faint enough to plausibly be an artifact of the star's own behavior rather than a genuine planetary signal. Additional observations were immediately scheduled. Confirmation would require more transits, more data stacked carefully against better stellar models before any confident claim could be published in a scientific journal with credibility intact. But for the first time in the entire Webb campaign on TRAPPIST-1, Something in the data pointed toward the existence of an atmosphere rather than its complete absence. The scientific community responded with measured, cautious acknowledgement. No announcements of confirmed habitable worlds, no declarations of life nearby. Just a careful recognition that the outermost habitable zone planet might have held on to something that the inner worlds had apparently lost across 8 billion years of slow attrition. Whether that something was enough for any known form of life to persist within it was the question that followed immediately and unavoidably, and the answer turned out to be considerably more complicated and more sobering than simple optimism could comfortably accommodate. Carbon dioxide in a planetary atmosphere is not a sign of life. That point needs to be stated plainly and clearly, because the temptation to read biological hope into any positive atmospheric detection around a potentially habitable planet is enormous, entirely understandable, and also potentially misleading. Carbon dioxide is produced by volcanoes erupting across a geologically active world. It is exhaled by animals as a metabolic waste product. It is released by industrial processes on a technological civilization's planet. It is also perfectly capable of existing in a thick, choking, completely lifeless atmosphere, as it does on Venus, where surface temperatures run hot enough to melt lead, and the atmospheric pressure at ground level sits 90 times heavier than what we experience at sea level on Earth. The potential carbon dioxide signal on planet G, if future observations confirm it as real, would tell researchers one significant thing. The planet has retained at least some atmospheric gas over its history. That is genuinely important information, especially given what the inner planets returned. But it would not tell researchers what else is in that atmosphere. It would not tell them how thick or thin the atmosphere is overall. It would not tell them whether the atmospheric pressure at the surface is hospitable or crushing. It would not tell them whether liquid water exists anywhere on the surface, and it would not tell them whether any biological process has anything to do with any of the gases present. To determine whether a planet's atmosphere carries genuine signs of biology, astrobiologists look for what they call biosignatures. These are atmospheric chemicals that are chemically unstable in the long term without a continuous source to replenish them. Oxygen is the most famous example. In the presence of ultraviolet radiation and reactive rock surfaces, free oxygen reacts away relatively quickly by geological standards. If a planet maintained substantial atmospheric oxygen without something continuously producing it, the oxygen would disappear over timescales short enough to matter. Life is the most efficient and well-documented source of atmospheric oxygen replenishment that science has yet identified. Methane is another important candidate. On Earth, the overwhelming majority of atmospheric methane is produced by biological organisms, from ancient microbes in wetlands to digestive processes in animals. Methane can also be generated by certain geological reactions, so finding it alone proves nothing definitively. But finding both oxygen and methane simultaneously in the same planetary atmosphere creates a particularly difficult to explain scenario. The two molecules react with each other and effectively destroy each other when they come into contact. If a planet maintained both simultaneously at detectable concentrations, something would need to be replenishing both of them continuously against their tendency to react away. Life is currently the only known process that could accomplish this efficiently and stably over long periods. Webb searched for these combinations in the TRAPPIST-1 habitable zone planets and found no clear oxygen signal, no methane signal, and no combination of molecules whose simultaneous presence would demand a biological explanation. The absence does not rule out life. Biology might exist there in forms too sparse or chemically subtle to register a detectable signal at 40 light years. But the story of TRAPPIST, one cannot conclude with discovery. It has to conclude, for now, with deeper and more difficult questions. When scientists first announced the TRAPPIST-1 system in 2017, they mentioned the star's estimated age almost in passing. During press conferences, and in the supporting footnotes of technical papers, 8 billion years old, roughly twice the age of our solar system. The number was noted by those paying close attention, filed carefully away, and then largely set aside as everyone focused on the astonishing headline about 7 potentially habitable planets waiting to be studied. But 8 billion years is not a footnote in this story. It is arguably the single most consequential number in the entire system, shaping everything that might have happened there and everything that might no longer be possible. Consider what Earth has looked like across its 4.5 billion years of existence. For the first several hundred million years, it was a largely molten world bombarded continuously by leftover debris from the violent early phase of the solar system's formation. Life did not appear in any form the geological record currently shows us until roughly 3.5 to 4 billion years ago, once conditions had stabilized enough for chemistry to begin organizing itself into something self-replicating and persistent. Since that beginning, life has had between 3.5 and 4 billion years to evolve from the simplest possible self-replicating chemistry to the entire complex biosphere that exists on this planet today. TRAPPIST-1's planets have had 8 billion years since their formation. If biology is capable of getting started on a rocky planet in a habitable zone around a red dwarf, 8 billion years is a span of time so extraordinary that its implications become genuinely difficult to frame in any intuitive way. It is twice the time life has had on Earth to go from single cells to everything alive today. The possibilities for what 8 billion years of uninterrupted biological and potentially cognitive evolution might produce, if conditions remained hospitable long enough, sit beyond our current vocabulary to describe with any confidence. But 8 billion years of potential biological time is also, by exactly the same arithmetic, 8 billion years of radiation bombardment from an active and magnetically volatile star. 8 billion years of potential atmospheric erosion washing over worlds with no protection. 8 billion years of tidal forces reshaping planetary interiors and potentially suppressing the protective magnetic fields those interiors might have generated. The same extended timescale that makes these worlds so tantalizing as hosts for deeply evolved life is precisely what makes them potentially so stripped and bare. The debate becomes one of timing above all else. Did the planets lose their atmospheres quickly, during the earliest and most violent period of the star's magnetic life, before biology had any realistic window to get established? Or did they hold on through that early violence, allowing billions of years of potentially habitable conditions during which life might have emerged and then adapted as conditions worsened? The difference between those two timelines is the difference between a system that never had a real chance and one that might still be quietly, stubbornly alive in places our instruments have not yet learned to look. The surface of a tidally locked, radiation-battered, potentially atmosphere-stripped planet is not an obviously hospitable place for a living organism to spend its days. The surface is simply where the story starts, not necessarily where it ends. Beneath the surface of a rocky world, shielded by kilometers of dense rock from whatever is happening in the atmosphere and the radiation environment above, a completely different world might exist, warmed by the planet's own internal heat, chemically active in ways that do not require sunlight, and potentially liquid where the pressure and temperature are right. On Earth, the deep subsurface is far more alive than most people realize. Bacteria and archaea, the ancient and extraordinarily hardy single-celled organisms that dominated this planet for its first 2 billion years, live kilometers below the surface in conditions of extreme heat, extreme pressure, and total, absolute darkness. They do not depend on photosynthesis. They do not require a connection to the surface environment at all. They feed on the chemical energy released by reactions between water and certain types of rock, a metabolic pathway called chemolithotrophy that has no requirement for sunlight whatsoever. The total mass of living organisms hidden in Earth's deep subsurface may be comparable to the total mass of all surface life combined. They are the hidden majority of our biosphere, largely invisible and almost entirely unstudied until the last few decades. On a planet like TRAPPIST-1 or F, this kind of life would not be merely possible in some abstract theoretical sense. It might represent the only form of life that could have survived the deteriorating surface conditions across billions of years of stellar bombardment. If the planet once had a thicker atmosphere and liquid water pooling on its surface, and if early biology got started during that more hospitable window, then as the surface became increasingly hostile over geological time, the survivors among those early organisms would likely have been exactly the extremophiles best adapted to burrowing deeper, following the water table down, retreating away from the worsening conditions above them. There is even a scenario that requires no surface atmosphere at all. If the interiors of these planets retain sufficient heat from their formation, or from the tidal flexing driven by the star's constant gravitational pull, liquid water could exist in pockets or layers deep underground, hidden beneath a frozen crust kilometers thick. Water that melts the underside of an ice shell from below, creating subsurface oceans completely isolated from the hostile surface above, is not a theoretical fantasy. It is essentially the situation that planetary scientists believe exists today on Europa, a moon of Jupiter, and on Enceladus, a moon of Saturn. Both are considered among the most promising places in our solar system to search for simple microbial life precisely because their liquid water environments are shielded from the harsh radiation environment of space. The TRAPPIST-1 planets might host similar subsurface environments, and if life began there billions of years ago and retreated downward as conditions worsened, Webb's atmospheric observations would miss it entirely. The telescope is designed to read chemical signals in the air and from the surface. It cannot see what is happening kilometers below the rock. Even our most powerful instrument might simply be looking in the wrong direction entirely. One of the most technically frustrating aspects of the entire TRAPPIST-1 campaign, and one that genuinely threatened to limit the scientific value of every Webb observation in this system, is a phenomenon that researchers call stellar contamination. The name sounds like a straightforward measurement challenge. In practice, it is a deeply complicated astrophysical problem that required some of the most sophisticated computational modeling in the history of exoplanet science to even begin addressing in a serious way. Here is the core problem. When Webb observes a planetary transit, it is measuring an extraordinarily subtle dimming of the starlight caused by the planet crossing in front of the stellar disk. By analyzing which wavelengths of that starlight dim slightly more than others during the transit, it can infer the presence and composition of whatever atmosphere the planet has, if it has one at all. But the star is not the simple, steady, uniform light source that the simplest possible version of this analysis requires it to be. The surface of TRAPPIST-1 is covered in regions of significantly varying temperature, cooler dark spots, and hotter bright patches called faculae that continuously shift, grow, shrink, appear, and disappear as the star's powerful magnetic field churns and reconfigures beneath the visible surface layer. When a planet transits across a dark, cool spot on the stellar surface, the measured dimming changes in one direction compared to what you would record from a transit across a uniform background. When it crosses a hotter and brighter facula, the effect runs in the opposite direction. Because TRAPPIST-1's surface is constantly evolving, its pattern of spots and bright regions shifting and reconfiguring over hours and days between transit observations, the baseline against which researchers are measuring the planetary atmospheric signal is never truly stable. It is always moving, always superimposing its own variations on top of whatever the planet itself is contributing to the observed spectrum. For relatively stable stars, this contamination effect exists but can be managed within careful modeling frameworks developed over years of observations. For TRAPPIST-1, which is extraordinarily magnetically active and variable even by red dwarf standards, the stellar contamination problem escalates into a major and difficult to remove source of interpretive confusion. Spectral features that look superficially like atmospheric molecular signatures can actually be artifacts generated by the star's own surface heterogeneity. building sophisticated and precisely calibrated models of the stellar surface variability and subtracting its contribution cleanly from the planetary signal requires data, computational resources, and modeling techniques that are still actively being developed and improved. This is one primary reason why essentially all published Webb results for TRAPPIST-1 have been reported with careful qualifying language. Phrases like possible signal or broadly consistent with rather than clear detection or confirmed presence appear throughout the literature, precisely because the margin for error introduced by stellar contamination is large enough to prevent confident interpretation of anything less than a very strong and unambiguous signal. More observations, more transit events, and substantially better stellar surface models are all essential before the atmospheric story of this system can be told with genuine scientific confidence and the certainty researchers are working toward. Before Webb launched and began its science mission, research teams distributed across dozens of institutions around the world had spent years constructing detailed atmospheric models for the TRAPPIST-1 planets. Every scenario that could be physically motivated and computationally modeled was considered and worked through with care. Thick carbon dioxide atmospheres modeled after Venus. Thin nitrogen-dominated atmospheres resembling what persists on Mars today. Earth-like mixtures of nitrogen and oxygen in various proportions and pressures. Hydrogen-rich inflated atmospheres that some theoretical models suggested close-in rocky worlds might retain under the right interior conditions. Steam atmospheres saturated with water vapor from evaporating ancient oceans. And at the most pessimistic end of the model space, bare rock worlds with no atmospheric envelope whatsoever, no gases, no chemistry, nothing between the surface and the hard vacuum of space. Each of these scenarios generated specific, testable predictions about what Webb should observe when it looked at the system. A thick Venus-like atmosphere would produce a characteristic thermal emission profile and a specific pattern of absorption features in the transmission spectrum during planetary transits. A thin Mars-like atmosphere would generate a different and much fainter set of signals. Earth-like composition would leave its own distinct molecular fingerprint. The bare rock scenario would produce results consistent with direct thermal radiation from the surface itself, with no atmospheric contributions at all. These predictions were worked out in precise mathematical detail before the telescope ever looked at the system, giving researchers a clear and principled reference map against which to compare the actual arriving data. What happened was that the real Webb measurements kept matching the most pessimistic corner of that carefully constructed reference map. For planets B and C, the bare rock models provided the most consistent and statistically convincing explanation of what the telescope measured. For planet E, the data was more ambiguous overall, but tilted uncomfortably toward minimal or absent atmosphere, rather than toward the middle ground scenarios that would have kept scientific optimism most intact. For planet G, a faint potential signal emerged that kept some possibility alive but was too uncertain to move the interpretation confidently away from the pessimistic end of the model menu. A minority position within the exoplanet habitability community had argued well before Webb launched that red dwarfs, despite their extraordinary lifespan and sheer numerical abundance in the galaxy, might be fundamentally incompatible with long-term atmospheric retention on close-in rocky worlds. The sustained flaring and radiation, they argued, was simply too aggressive and too relentless across too great a timescale for small planets to maintain the atmospheric envelopes that surface habitability requires. The Webb results were providing this minority position with its most significant empirical support in the history of the field. The majority of researchers were not ready to declare the question closed. They pointed to instrument limitations, to stellar contamination uncertainties, to the need for substantially more observations, and to the genuine possibility that habitable conditions might exist in subsurface or atmospheric environments that current techniques cannot reach. One more diagnostic approach remained to be fully exploited before the picture could be considered as complete as current capabilities allow. Among the most elegantly diagnostic tests available to Webb for studying tidally locked planets is the measurement of temperature contrast between the permanently sunlit hemisphere and the permanently dark hemisphere. This might sound like a simple side-by-side comparison, but the information it encodes about atmospheric conditions is profound and difficult to replicate with any other technique available at these distances. The underlying logic is straightforward once you think through the physics carefully. On a planet with no atmosphere, heat has no efficient mechanism to travel from the day side to the night side. Without air, without wind, without the circulation of gases carrying thermal energy around the globe, the physics of heat transfer become limited to radiation and conduction through rock, both of which are far too slow to meaningfully equilibrate temperatures across the surface of an entire planet. The sunlit hemisphere absorbs starlight and heats up to whatever temperature the direct radiation dictates. The dark hemisphere sits in absolute darkness and cools to whatever temperature the slow loss of stored heat allows. The result is an extreme temperature difference between the two hemispheres, potentially ranging across hundreds of degrees. On a planet with a thick, active atmosphere, the situation is almost the opposite. Winds, driven by the pressure and temperature gradients between the hot day side and the cold night side, circulate air continuously and energetically around the globe. Heat moves with those winds from the sunlit hemisphere to the dark hemisphere, partially equalizing the temperatures across the surface. The thicker and more thermally active the atmosphere, the more effective this heat redistribution becomes and the smaller the temperature difference between the two hemispheres grows. Venus provides the most extreme example in our own solar system. Despite its very slow rotation, meaning one hemisphere is exposed far longer than the other at any given time, the surface temperatures on Venus are nearly identical all the way around the globe. Its enormously thick carbon dioxide atmosphere redistributes heat so efficiently that no measurable gradient remains at surface level. For the TRAPPIST-1 planets, this day-night temperature contrast serves as a direct and interpretable measure of atmospheric thickness and activity. Webb's mid-infrared instrument detects this contrast by tracking how the total brightness of the star plus planet system changes as the planet moves through different orbital phases, presenting progressively different fractions of its day and night sides to the telescope over time. The contrast measurements for the inner TRAPPIST-1 planets were consistent with large temperature differences between the hemispheres, pointing directly toward minimal atmospheric heat redistribution, exactly as the bare rock scenario predicts. The night sides of these worlds appeared cold in a way that matched what you would expect from uninsulated rock, with nothing to ferry warmth from the daylit side to the dark. The outer planets have been harder to measure this way because their longer orbital periods reduce the frequency of complete orbital phase observations. But as Webb accumulated additional data, the pattern for the inner system grew harder and harder to argue against. Something had claimed the heat from the night side of these worlds, leaving them dark and cold in a way that pointed toward one explanation above all others. TRAPPIST-1 has forced a long brewing reckoning with something astronomers had been quietly and sometimes heatedly debating for well over a decade before Webb ever left the ground. Call it the habitability paradox of red dwarf stars. On one hand, red dwarfs are the most common type of star in the galaxy by an enormous margin, comprising roughly 70 to 80% of all stellar objects in the Milky Way. If life requires a rocky planet in a habitable zone, and red dwarfs host plenty of those simply by virtue of their sheer numbers, then basic statistics suggest the galaxy should be filled with potential homes for biology distributed among the most abundant stars. On the other hand, red dwarfs are precisely the type of star that creates the most challenging conditions for habitability to be achieved and maintained over the timescales biology actually requires. They are magnetically violent, particularly during their extended active youth. They flare with disturbing frequency and intensity across their entire multi-trillion-year operational lifespans. Their habitable zones sit so close to the stellar surface that any planet sitting in those zones is almost certainly tidally locked. Planets there must survive a sustained and relentless radiation environment that challenges even the most optimistic atmospheric retention models built from our current understanding of planetary physics. The paradox resolves one of two ways, and the scientific community has been genuinely and sometimes heatedly divided between them for years. One resolution is that red dwarf planets can and do retain their atmospheres despite the radiation environment, protected by strong magnetic fields, replenished by sustained geological activity, or shielded by some combination of mechanisms that current models do not yet fully capture. If this is true, the sheer abundance of red dwarfs translates directly into an enormous abundance of genuinely habitable worlds, and life in the galaxy might be common by any reasonable definition. The other resolution is that the radiation environment around red dwarf stars is effectively insurmountable for atmospheric retention on close-in rocky planets across the geological timescales involved. That stripping happens faster than replenishment, that the most common stellar environments in the universe are, by a quiet irony of physics, among the least compatible with sustained surface-based biology. If this is true, life-hosting worlds might be largely concentrated around the less common but more radiation-gentle stellar types, and the actual number of genuinely habitable planets in the galaxy could be orders of magnitude smaller than the raw count of red dwarf habitable zone planets implies. Webb's observations of TRAPPIST-1 represent the first serious, direct, telescopic evidence to genuinely inform this debate at the level of precision the question demands. The evidence so far fits the second resolution considerably more comfortably than the first. The most celebrated and intensely studied, potentially habitable system ever discovered is looking, in the unsparing light of actual measurement, considerably less hopeful than the excitement of 2017 suggested. One system cannot close a debate about an entire galaxy, but this one has irrevocably changed the terms of that conversation in ways that will shape how the field thinks and plans for years to come. Webb is an extraordinary scientific instrument representing the culmination of decades of engineering ambition and international collaboration. But it is absolutely not the final word in this story, and every researcher studying TRAPPIST-1 is operating under the clear understanding that it cannot be. Astronomy has always been a science defined as much by the instruments it is currently building as by the ones it is currently using, and the questions Webb has sharpened around the TRAPPIST-1 system are already driving design decisions and funding arguments for the next generation of observatories that may eventually answer them with the confidence the current data cannot provide. The extremely large telescope currently under construction in the Atacama Desert in Chile will, when completed, possess a primary mirror spanning 39 meters across. For comparison, the primary mirror on Webb spans just over 6 meters. The extremely large telescope will be capable of directly imaging some nearby planetary systems rather than relying solely on transit and eclipse measurements, and it will analyze atmospheric spectra through high-resolution spectroscopy techniques that can distinguish between planetary and stellar signal contributions in ways that even Webb cannot achieve from its orbit. Whether this capability will prove sufficient to resolve the atmospheric ambiguity around TRAPPIST-1's outer planets depends on what is actually there and how strong the true signal turns out to be, questions that only future measurements can answer. The Habitable Worlds Observatory is a space telescope concept currently under detailed study at major space agencies around the world, with broad scientific support behind it. Designed specifically to directly image Earth-like planets around nearby solar-type stars and characterize their atmospheric chemistry for genuine biosignature combinations. It would not primarily target TRAPPIST-1, since that system orbits a red dwarf rather than a solar-type star. But the technological advances required to build and operate the Habitable Worlds Observatory will push the boundaries of what is achievable in exoplanet atmosphere science across the board, and those advances will eventually benefit the study of every interesting planetary system, including this one. More immediately relevant are additional Webb observation campaigns on TRAPPIST-1 that are already planned, and several of which are actively underway. The potential carbon dioxide feature on Planet G needs confirmation through many more transit observations before it can be confidently published as a genuine detection or definitively ruled out as a stellar artifact. Better stellar surface models that more precisely characterize and subtract TRAPPIST-1's own variability from the planetary signal are being developed and tested against the accumulating data. The scientific campaign on this system is not finished by any measure. Radio telescopes are also being pointed continuously at the TRAPPIST-1 system in a sustained and carefully planned search for magnetic activity signatures from the planets themselves. A confirmed magnetic field detection around any of the habitable zone planets would substantially change how researchers interpret all the atmospheric measurements collected so far and would reopen possibilities. The current data appears to be closing. The question of whether any of these worlds retained sufficient magnetic protection across 8 billion years of stellar bombardment remains one of the most consequential open questions in modern exoplanet science, and answering it has become a stated priority for multiple independent research programs currently operating around the world. Every time humanity examines a potentially habitable world and finds it less welcoming than hoped, the same ancient philosophical question rises quietly to the surface of scientific conversation. If life is possible in the universe, and if the physical conditions necessary for it seem to exist in many places across a galaxy of hundreds of billions of stars, why have we found no evidence of it anywhere beyond Earth? Why, in all the signals we have listened for and all the skies we have surveyed, has nothing answered back? This is the core of what has come to be called the Fermi paradox, named for the physicist Enrico Fermi, who reportedly raised the question simply and directly during a casual lunch conversation in 1950. If the galaxy should be full of life, where is everybody? The TRAPPIST-1 results have added a new and significant layer to that old and unresolved question. For years after the 2017 discovery announcement, red dwarf systems were one of the most popular proposed solutions to the paradox. The galaxy is filled with red dwarfs. They last almost incomprehensibly longer than stars like our own. Their habitable zone planets are, because of their tight orbits, actually the easiest category of rocky world for current telescopes to study. If life is going to be common in the galaxy, it seemed almost inevitable that it should be most common around red dwarfs, simply because red dwarfs are most common. Some researchers went so far as to suggest that if any alien civilizations existed in our galactic neighborhood, they almost certainly orbited a red dwarf star. Webb's findings complicate that reasoning in a way that is difficult to dismiss. If red dwarf radiation environments systematically strip atmospheres from close-in rocky planets faster than those atmospheres can be replenished, then the most common type of star in the galaxy produces the least hospitable category of habitable zone planet. The sheer numerical abundance of red dwarfs in the galaxy would not translate into an abundance of actual life-hosting worlds, but into an abundance of sterile, radiation-scoured rocks that once sat in theoretically habitable zones and then lost everything needed to actually be habitable. That would substantially narrow the window available for life in the galaxy. Yellow dwarf stars like our own, which provide more stable radiation environments and whose habitable zones sit at distances comfortable enough to allow a planet to avoid tidal locking, make up a much smaller fraction of stellar objects. If life requires that particular combination of circumstances, rather than being able to thrive around the most common class of star, the number of life-hosting worlds in the galaxy could be orders of magnitude smaller than the most optimistic estimates from earlier decades suggested. But the caveat that applies here cannot be overstated. We have looked at one system in one corner of one galaxy and found results consistent with one possible resolution of the habitability paradox. Drawing sweeping conclusions about the distribution of life across the entire observable universe from that single observational campaign would be exactly the kind of reasoning that has led astronomy badly astray before. TRAPPIST-1 is important. It is not the last word. There is something quietly and unexpectedly affecting about sitting with the current picture of the TRAPPIST-1 system long enough to really let it settle into focus. These are not strange, incomprehensible objects with no relationship to anything in our experience. They are rocky planets built from the same chemical inventory that built Earth. They are nearly identical to Earth in size. They orbit in the band of distances where temperatures permit liquid water by the same physics that applies here. They had, by all the standard criteria that scientists have developed across decades for evaluating planetary habitability, every structural prerequisite we currently know how to measure and quantify. And 8 billion years ago, when the system was newly assembled and the star was still settling into the long, slow, patient burn of stellar middle age, at least some of them might have had surface conditions that were genuinely, unmistakably hospitable. Models of early red dwarf stellar evolution suggest that young red dwarfs are actually somewhat more luminous than they become after settling into their mature configuration. The star dims gradually over the first billion years or two of its life as its internal structure reaches a stable equilibrium. For the TRAPPIST-1 system, this means the habitable zone planets may have received different energy inputs during their early history than they receive from their star today. Some models suggest there might have been a window of relative stability, perhaps lasting hundreds of millions of years, when surface conditions on the inner habitable zone planets were more genuinely favorable than any current measurement indicates. The flaring activity of red dwarfs also changes with age in ways that matter for this question. Young red dwarfs produce far more aggressive and frequent flares than mature ones. The first several 100 million years of TRAPPIST-1's existence were almost certainly more violently magnetically active than the 8 billion-year-old star we observe and measure today. The planets may have survived the most intense period of radiation bombardment in their history during that early window and held on through it in some form, only to have the slower and more patient erosion of subsequent billions of years gradually complete what the early violence started. If that general timeline is approximately correct, a physically motivated scenario rather than a confirmed finding, then the TRAPPIST-1 habitable zone planets might have had surface conditions capable of supporting liquid water and complex chemistry for a period of time broadly comparable to the window in which life first appeared on Earth. Whether that was long enough for biology to organize itself from raw chemistry, whether the radiation was already too damaging for any organic chemistry to persist even in that early period, whether some other factor foreclosed the possibility entirely, is something we cannot determine from 40 light years with any instrument currently available or planned. What can honestly be said is that these worlds are not the victims of obvious, immediate impossibility. They are worlds that had a plausible chance. Something, most likely a combination of geological time and stellar violence, apparently took that chance away before anyone on Earth knew to look for what might have been there. They are, in the most literal and accurate sense of the phrase, the planets that might have been alive. Most scientific discussion around the possibility of life in the TRAPPIST-1 system centers on biosignatures, the chemical fingerprints that biological processes leave embedded in a planet's atmospheric composition as a direct consequence of metabolic activity. But there is an entirely different category of observable signal that the broader scientific search for intelligence beyond Earth considers worth pursuing alongside biosignatures. These are called technosignatures, and they refer to evidence, not just of life in the basic biological sense, but of life that has developed technology sophisticated enough to leave detectable traces in its environment that persist across astronomical distances and point-ply timescales. The reasoning for considering technosignatures in the context of TRAPPIST-1 begins with the timeline available. If life emerged on any of the habitable zone planets during an early hospitable period and then had 8 billion years to develop without catastrophic extinction, the possibility of technological civilization arising at some point within that extraordinary span is genuinely not zero. It is not even obviously remote, given what biological complexity on Earth has achieved in approximately 4 billion years, starting from nothing more than self-replicating chemistry. A civilization that had an additional several billion years of development beyond what we currently represent would be so profoundly different in its technological capabilities that our current methods for detecting or conceptualizing it might be fundamentally inadequate for the task. Of course, this reasoning depends entirely on the foundational assumption that life actually existed on one of these worlds at some point, which remains completely open and unconfirmed. But regardless of how the habitability debate ultimately resolves, TRAPPIST-1 has been included in serious technosignature search programs for years. Radio telescopes scanning for narrow-band artificial transmissions, the kind of engineered signal that would most clearly distinguish itself from any known natural astrophysical process, have been pointed at the system as part of broader, targeted survey campaigns. None have returned anything that could not be explained within the framework of natural processes and instrument noise. That absence is not particularly informative given the vast space of possible signal frequencies, encoding schemes, and directional possibilities that would need to be comprehensively searched before a null result carries real weight. What is more conceptually interesting from a technosignature perspective is the idea that a truly advanced civilization, one that had developed technology across even a fraction of the 8 billion years available, might have modified its environment in ways that go far beyond the kind of atmospheric biosignatures Webb is designed to detect. Large-scale planetary engineering, energy harvesting at stellar scales, the detectable waste heat from information processing at enormous computational scales, are all theoretically detectable phenomena that future instruments with broader observational capabilities might be able to identify and recognize against natural backgrounds. Webb was not designed with these searches as a primary mission objective, but the atmospheric chemistry baseline measurements it produces for the TRAPPIST-1 planets establish reference points against which future researchers can compare any anomalous results that resist natural explanation. The gap between what established physics predicts and what observation actually records is always where unconventional discovery, if it ever comes, will first appear as a question worth investigating. The story unfolding around TRAPPIST-1 is not, in any meaningful sense, confined to 7 planets orbiting a single dim star 40 light-years from Earth. It is the story of what happens to rocky worlds around the most common class of star in the galaxy when geological time runs long enough to reveal the truth of the radiation environment those worlds must survive. And the implications of what Webb's observations are revealing extend far beyond this one system into the most fundamental questions about the distribution of life, if it exists anywhere beyond Earth, across the Milky Way. If the pattern Webb is documenting around TRAPPIST-1 holds more broadly across other red dwarf planetary systems, which the underlying physics suggests may be at least partially plausible, then the galaxy's most abundant category of real estate might be largely uninhabitable at the surface by the standards we currently understand life to require. The hundreds of billions of red dwarfs comprising the majority of the Milky Way's stellar population might each host rocky planets in habitable zones, and those planets might, in a large fraction of cases, have lost the atmospheric conditions necessary for surface liquid water before biology ever had a realistic window to establish itself and persist. That would not mean the galaxy is empty and silent. It would mean that whatever life exists there is distributed very differently from what the most optimistic models from a decade ago suggested. Rather than being concentrated preferentially around the most abundant stellar type, it might be concentrated around the less abundant but more radiation-gentle stellar classes. the warm orange and yellow dwarf stars that offer more stable magnetic environments and habitable zones at orbital distances comfortable enough to avoid the tidal locking and sustained radiation exposure that characterizes red dwarf systems. Stars in this category are less common than red dwarfs, but still present in enormous numbers across the galaxy, making up a meaningful minority of the total stellar population. Viewed through this lens, our own solar system begins to look like a somewhat more specifically privileged environment than naive planet-counting statistics would suggest. Not unique in any absolute sense, almost certainly not the only example of its kind in a galaxy this large, but not as representative of the typical planetary environment as the sheer commonness of red dwarfs once seemed to imply. The interlocking combination of factors that made Earth habitable across 4.5 billion years, a magnetically moderate parent star, a planet at a comfortable orbital distance, geological cycling that continuously refreshes the atmospheric chemistry, a strong protective magnetic field generated by an active interior, might represent a more specifically demanding recipe than the raw abundance of rocky planets in habitable zones appeared to suggest during the optimistic first decades of exoplanet discovery. TRAPPIST-1 was meant to demonstrate convincingly that the conditions for life could be found essentially everywhere throughout the galaxy. What it may actually be showing us is that those conditions, in the sustained and interlocking form that life genuinely requires, are harder to assemble and maintain than counting planets alone could ever reveal. Science does not end with discouraging data. It redirects. It refocuses on sharper questions with better instruments. The history of astronomy is filled with moments when a beloved and carefully constructed hypothesis collapsed under the weight of new precise measurement, only for the scientific community to regroup and discover that the collapse itself had revealed something more interesting and more profound than the original hypothesis could have delivered. TRAPPIST-1 is not finished as a scientific subject because Webb returned results more sobering than the headlines of 2017 prepared people to expect. There are several active directions in which the science is continuing to develop and advance. Better models of TRAPPIST, one's own stellar surface variability, are being constructed and refined by multiple independent groups working from the data Webb has already accumulated over multiple observation campaigns. If researchers can more precisely characterize and subtract the star's own contribution to the planetary spectra, weaker atmospheric signals currently hidden below the noise floor might become visible against the corrected background. The potential carbon dioxide feature observed on planet G could resolve into either a confirmed detection or a definitively eliminated artifact with additional observations. Either outcome would substantially advance the field, and both would be, in their own ways, equally scientifically valuable. The TRAPPIST-1 planets are also being studied for signs of ongoing geological activity independent of atmospheric chemistry results. If any of them remain volcanically active today, fresh gases are continuously being injected into whatever thin atmospheric envelope survives, replenishing it from below even as stellar radiation strips it from above. Whether geological replenishment can keep pace with that stripping rate depends on interior heat outputs that current instruments cannot directly measure at interstellar distances. Some theoretical models suggest this balance could be achievable under the right interior conditions, which would mean that Webb's atmospheric measurement limits might reflect instrument sensitivity rather than true planetary emptiness. The subsurface water question remains entirely open and is likely to remain so for the foreseeable future. No current or near-future instrument can directly probe the deep interior of a rocky planet 40 light-years away for liquid water reservoirs. But indirect gravitational measurements derived from very precise orbital timing might eventually provide useful constraints on interior structure and water content for some of the TRAPPIST-1 planets as observational precision continues to improve. The search for magnetic field signatures through radio emission from the planets themselves continues without a confirmed result pointing in either direction. A confirmed detection of a functional planetary magnetic field around any of the habitable zone worlds would immediately and substantially change how scientists interpret every atmospheric measurement so far published about this system. The story of TRAPPIST-1 is genuinely not finished. It has become more complicated, more carefully uncertain, and therefore more scientifically alive than it was before Webb turned its mirror toward this small, dim, extraordinary star and looked closer than anyone had managed before. The next few years of observation, modeling, and instrument development will either confirm the sobering picture that has emerged or reveal that we were missing something important. Either possibility deserves the full and serious attention of the field. After all the transit measurements and thermal emission profiles, after all the spectral analysis and stellar contamination corrections, after all the debates about magnetic fields and tidal locking and subsurface oceans and the age of a star and the patience of geological time, the TRAPPIST-1 story circles back to a question that predates every telescope ever built. Are we alone in this universe? It is a question that human beings have been asking in one form or another for as long as there have been human beings capable of looking up at the night sky and wondering what else might be out there looking back. Webb was not built to answer that question definitively and finally. No single instrument, no matter how powerful, could be. But Webb was built to sharpen the question, to narrow the territory of genuine uncertainty, to replace informed speculation with precise measurement, wherever precise measurement was achievable. And in that mission, it has succeeded absolutely, even when the measurements returned were not the ones the scientific community or the broader public had been hoping to receive. What TRAPPIST-1 has taught us, in the most fundamental terms, is that being in the right orbital zone is necessary, but nowhere near sufficient for a world to actually be habitable across the timescales that matter for biology. The habitable zone defines where temperatures are theoretically compatible with liquid water, but whether water actually persists on a surface, whether an atmosphere holds together across billions of years, whether a planet maintains the conditions necessary for chemistry to organize itself into something alive and to keep that life going long enough to become complex, depends on an interlocking cascade of additional factors that have nothing to do with simple orbital distance from the parent star. The star's magnetic character matters enormously. The planet's own magnetic shield matters enormously. The planet's geological activity and the rate at which volcanism refreshes the atmospheric inventory matters. The planet's internal heat budget and how it interacts with the tidal forces from its star matters. The timing of when the atmosphere formed and when the most intense stellar activity occurred matters in ways that are sensitive to differences of hundreds of millions of years. Life, if it is rare, may be rare not because the basic chemical building blocks are scarce, but because the very specific and interlocking combination of conditions necessary to produce it and then sustain it long enough for complexity to emerge is more demanding and more difficult to assemble simultaneously than the abundance of process. Rocky planets in habitable zones might optimistically suggest. TRAPPIST-1 passed every paper test we designed for it. 7 rocky worlds, 3 in the habitable zone, a star that will outlive our own by a factor of nearly 2,000, 40 light-years away, close enough to study in detail with instruments we have actually built and launched. Then Webb looked closer with precision we had never before achieved, and the universe delivered the kind of answer it has always delivered to those who look carefully enough to receive it. Honest, complicated, more interesting than expected, and pointing unmistakably toward the next question rather than the last one. The search continues. It always does. And it always will, for as long as there are people who cannot stop looking up.